Hey, all right, workshop students. I got a question here on this. Looks like it's adding vectors together. It says here two forces acting upon an object. We've got a force of magnitude 1 at some direction theta 1 and a force of magnitude 2 at a direction of theta 2. The net force on the object has a magnitude of net force and is in direction of theta net. So let me start off with maybe a little lecturing here. This is how you would add two forces together. Let me maybe draw a little picture here. So if I had a grid, and I said, okay, here's my X and Y axis. And I said, all right, let's add up the first force. And maybe I'll change colors and even draw it as the numbers here. So F1, they don't give me a number how big it is, but it is at 157 degrees. Now, there's a lot of ways of measuring angles. Traditionally, it's from the x-axis, counterclockwise positive. So without other information, I would assume that that's what the author wants here. So let's see. Here's the x-axis. 90 degrees is straight up. 180 degrees is over here to the left. And so 157 would be off at this direction somewhere. And maybe I'll just make a dotted line because I really don't know how long to draw this because this problem doesn't say how big F1 is, just the angle. Now, the other one, they do say how big it is. It's about 355, and it is at an angle of 304 degrees. So let's see, 304. Right here would be 290, I think. Let's see, 180 and another 90 is 270 is what, 270. And so another 30 would make about 300. And so this, I guess, is the net. I'm sorry, this is force number 2, okay? And so we're supposed to add these two together, according to this. And so we're going to add these two together and get then this direction. And this is 246 degrees. So roughly 240, let's see, this would be 180. So we're looking at another 60. So we're looking at a result coming along here. But again, we don't know how big it is. Now, what I'm doing now isn't really necessary to solve the problem. But if you wanted to visualize it a little better, this is a nice way to do it. So let me take the one we do know, which is force number 2 at this angle like that. And then the one we don't know how long it is would be in that direction. Let me add it at the, and kind of visually move it to here. So we call what we call head to tail drawings. And so when you draw head to tail, the result of those two is then what it would visually look like. So if I draw the first one and I add the second one. So I draw the second one where the first one picks up. So this is actually the second one. So let me draw the second one first, and then I'll draw the first one where the second one ended. And it's supposed to touch this line back here at this angle. So this distance here must be the magnitude of the net. And this length, which in my drawing looks like it would be roughly the same as this drawing. Of course, I'm just kind of hand sketching it. But what that would tell me is, my guess is that the magnitude of F1 is somewhere around the same value as F2. Well, maybe it looks a little smaller. And then the magnitude of the net is significantly smaller, maybe a third of this, so maybe around 120-ish or something. So those are the two things we don't know. Now, mathematically, then we have x components and we have y components. And so if we add x components together, we would do something like this. We would have f1 and how much of it is on the x-axis, and f2, how much of it is on the x-axis. And when you add those together, you get the net force, and then how much of the net force is along the x-axis. So that's what your author is trying to help you with this problem. You don't even have to derive that. So there is that first statement. And in the y direction, you again would add up the y components. So there's how we get the y ones. And then we get the y component. And again, same idea. We just take the sign of all of these. And so those are our system of equations. Now, this first 6 minutes, I hope I didn't waste too much of your time, but that was more of a lecture on what you're trying to learn. Net force, what do they look like? How do you draw them? And then, how do you combine x components? How do you combine y components? Because in this problem, the author actually gives you this statement. So you don't need to really draw it, and you don't really need to come up with this equation. So I'll put this off to the side, and I'll just do the problem as probably intended, is to say, all right, this is unknown net force, so that's one unknown. I then have cosine of the net force, which is the 246 degrees. That is equal to the magnitude of F1 and the cosine of 157 degrees. Then we have force number 2, which is 355, and we have then the cosine of 304 degrees. And if we put all that together, let me just see if I'm in degrees mode, and put in some numbers here, and take cosine of 246, I get a negative 0.407, and net force is one of the unknowns. The cosine of 157 is negative 0.921 F1. And this is 355 times cosine of 304, which is 198.5. So let me put a little box around that, because I guess that would be our first equation with two unknowns. We don't know the net force and we don't know F1. And taking the second equation, which says net force times the sine, and so I'll put the sine of 246 degrees there. Again, times F1, which we don't know, but then sine of 157 degrees. For this problem, I think you guys get different numbers depending on who's doing the problem. Plus 355 times the sine, so 355 times the sine of 304. Okay, and then putting those into your calculator. So I've got sine of 246. 246. That just seems a little high, but I typed it right, 246. Okay, so negative 0.913 times the net force. And then sine of 157 is 0.391 F1 plus 355 times sine of 304, which make a negative 294. And so I'll circle this because this is then the second equation. And you might say that's the physics part of this problem, was just kind of understanding why we even have these equations, and then given these four pieces of information, we can plug them in, and now we have two equations and two unknowns. And so now it just becomes a math step, if you will. Maybe I'll do this. Maybe I'll just solve this first one for net force. And I would get that by taking the 0.391 and dividing it by the negative 0.913 and get a negative 0.428 F1. And then this would be the negative 294 divided by a negative 0.913 and come out to a plus 322. And then use that in this equation. So minus 0.407 times the net. Negative 0.428 F1 plus 322 equals negative 0.921 F1 plus 198.5. And then when I do the distributive property here, this negative times that negative make a positive 0.407 times 0.428, making a 0.174 F1. And then this negative 0.407 multiplied by 322 come out to be a negative 131. This is a negative 0.921 F1 plus 198.5. All right, now with a little bit of manipulating the numbers, why don't I put my F1s together? So 0.174 is a positive. When I bring this over, it comes a positive 0.921. And so this is 1.095 F1. And then this 198.5 added to 131 comes out to be 329.5. And so F1, so let's see, 329.5 divided by 1.095 comes out to be about 301. So I get 301, and as mentioned earlier, that kind of matches what I was kind of trying to draw. F1 down here looks like it would be about the same amount, maybe a little shorter. And so F2 was 355, and F1 then comes out to be 301. So good. Now, I guess technically I'm done with the problem, but it couldn't hurt to then answer the second part, that what would be the net force. And so I can come back to any of these equations, and I'll just come back to this one. This would be the negative 0.428 times this F1, which we said was 301, and then add to it the 322, and we get a value of 193 for the net force, which again matches this picture pretty well. I said about a third, and so I was putting it around more like 120-ish, but it's in that ballpark there of 193. So there is hopefully a helpful video. Bye now.